Good morning, young people. Today we're going to be talking a little bit more on solution stoichiometry, and we're going to be talking about types of reactions so that we understand that and take that a little further. So some of it's going to be review, some of it is going to be new. So vocabulary reactions, chemical reactions versus chemical equations. Some people get these two sort of mixed up. They use them synonymously, and they probably shouldn't be, because a chemical reaction is a description of how elements or compounds are transformed into new substances, whereas a chemical equation needs to be balanced because we need to show relative amounts of reactants and products. We're not just showing the change, we're showing a lot more. It also gives us the phase symbology, SLGAQ. That's representative of solid, liquid, gas, and an aqueous solution, respectively. And one other thing that we have to be aware of is that there's no energy or time ever alluded to regarding reactions here. When we see a chemical reaction, it doesn't tell us how much time that took. It doesn't tell us how much energy was released or taken in. None of that is included in the balanced chemical equation. Anton Lavoisier came up with the law of conservation of matter years and years and years ago. As you can see, his date of birth and date of death there. And he said matter can neither be created or destroyed. He was doing all kinds of experiments, and all these experiments kept coming out the same, that how much ever he put in, he got out. And he started to put these things together and say, okay, I can't create or destroy matter. And so balancing equation is really all of Lavoisier's fault. So if you want to blame someone for having to balance equations appropriately, blame Lavoisier. Other people came along and helped him, but he was the first guy. So types of chemical reactions. The first type of chemical reaction is synthesis. Two or more simple substances form a more complex one. That's A plus B yields AB. Notice there is only a single product. And that's how we recognize it. We recognize it because it is a single product. So we need to make sure we understand that. So I'm going to turn myself off because I'm going to be in the way in just a second. So here we go. One example of a synthesis reaction is the combination of magnesium and nitrogen to form magnesium nitride. So here we see these elemental forms, and then we see a single product. One single product. Okay? Again, oxygen and hydrogen coming together to yield water, which is more complex. We have hydrogen, we have oxygen, and we have water, which is more complex. We have one product. One product, okay? I want you to also notice we're saying element, and these are not necessarily elements. We consider them the elemental form of these things. Remember, Brinkelhoff. This is going to be really important that you remember this. Brinkelhoff are the 7 elements that are never found as single atoms. They are only found as diatomic molecules. And when we speak of them, when most chemists speak of them, they call them the elements. And I want you to understand that they're really not elements. They're the elemental form. That's the only way we see them. So those things are only seen in that respect. So please make sure that you have that understanding. Okay. Next type of reaction is a decomposition reaction. In a decomposition reaction, it's the opposite of synthesis. Basically, we have a more complex substance breaking down into simpler substances. So AB, a single reactant. That's going to be the way we recognize it, going to A plus B. So one example of this is the decomposition reaction of hydrogen peroxide. We're actually going to be talking about that a little later, and we're going to be doing a redox titration with hydrogen peroxide. Okay, so be aware that we are going to talk about that. And we know that hydrogen peroxide comes to us in a brown bottle from the store. And that is because this reaction happens in UV light. So when UV light hits hydrogen peroxide, it breaks down into water and oxygen gas. Okay, so it's very light sensitive, so we put it into a brown bottle because it's light sensitive. Next type. Combustion reactions, and these may be a little out of order in your notes, so just be aware. A combustion reaction involves any reaction between any combustible material and an oxidizer to form an oxidized product. I know that you're like, oxidizer, oxidized product. That sounds a whole lot different from first year. That's because we're trying to correct a misunderstanding that we presented. Oxygen is the most famous oxidizer. Yeah, okay, sure. The products of combustion reaction are simply oxides of substances combusted. So, unfortunately, Most of the examples that you've seen involved hydrocarbons like methane or octane or other kinds of hydrocarbons. And so you have this understanding because we were seeking out a logarithm to be able to, an algorithm to be able to make sure that we knew how this happened all the time. So basically, students are thinking that the only products of combustion reactions are CO or CO2 and water, the oxides of carbon and hydrogen, because we've always done hydrocarbon combustion. However, on the AP exam, they're going to expect that you know combustion reactions can occur for anything. So for example, magnesium ribbon burns in air. We've seen this happen. You see it when you use a sparkler. And the silly answer that is written here is that Mg plus O2, notice the O2 there, yields CO2 and water. But the problem is there's no C and there's no H anywhere on the reactant side, so you can't really do that. The correct answer is here. We get the oxide of magnesium. So this not only is a synthesis reaction, but it's also a combustion reaction. So some of you recognized this first year, some of you didn't. We led you to believe that combustion reactions were a lot simpler than they are. Combustion reactions can happen anytime something has an oxidizer and is basically combusting with that oxidizer. Okay? So just be really careful about that and really be careful about the way you talk about that. So most people think that combustion means burning, literally. But cellular respiration involves the most famous of the combustion reactions, the absolute most famous of them. So let's talk about that just a little bit. We know that it is glucose plus oxygen yields CO2, H2O, and energy. This is how our body achieves the energy process. We see it here. Here's the energy right there in the form of ATP. Okay? But this isn't burning. We're not on fire when this is happening. And why does that happen? Well, it happens because we have a huge number of enzymes that are lowering the activation energy of all of the steps that are involved in this process. You all know by now because you've had biology class, or some of you haven't yet, but you should know by now, most of you should be figuring out by now, this process is not a single step. This is multi-stepped. This is a multi-step chemical reaction. And in this multi-step chemical reaction, at each point an enzyme comes in and plays a part, and it lowers the energy to get the reaction going. And that energy is called the activation energy. Okay, we're going to be dealing with this a little bit more later. The activation energy is the energy to get, lowers the energy to get the reaction going. Okay? And that's called the activation energy. And so each time an enzyme comes in and lowers that energy, it literally takes the energy down, so there is no burning. And that is required because if we burned every single time we made energy, we'd be in trouble. Okay? So while we're doing something with a campfire or we're doing something on our stove, we're not having enzymes lowering activation energy. And so it's very easy to burn things, literally burn things. But in our body, the burning is a little different because we can't be on fire. So we have to lower activation energy in order for that to happen. So each time one of these steps occurs, an enzyme comes in and helps to lower the activation energy. Okay? Pretty interesting when you think about it. And we're going to be talking about enzymes a little bit later, and this idea of activation energy and what that means, and all kinds of different things. So you're going to get an understanding of all these things a little bit more later, but I want to introduce them because I want you to understand that occurs. Okay, so a single replacement reaction. Oops, I messed up. Okay, a single replacement reaction, a single uncombined element replaces another element in a compound. So we have A, which is our element, and we have a compound BC, and A replaces the appropriate portion of BC to form AC, and then the compound B comes out by itself. So one element trades places with another element in the compound. Typically this is an ionic substance, but it doesn't have to be. When it's ionic, it's very easy to determine because A must be a cation and it must replace the cation B. But when it's a molecular compound or a covalent compound, a little bit more difficult, but it's still the same concept. Okay, so an example of this is when zinc metal replaces hydrogen in the hydrochloric acid. So zinc is going to be our cation, hydrogen is the cation here, so zinc will come, hydrogen will come out, we get zinc chloride in aqueous solution and hydrogen gas. And we can see that in the bubbling. Do you see all of this bubbling right here in this test tube? We've seen this reaction multiple times, okay? All right, so by the way, this symbol right here, this upward arrow symbol, is just another way to signify a gas is being produced. So now we have another symbology that helps us to understand what's going on there. Second one, or the last one, is double replacement reactions, and as I said, these are a little out of order. The anions and cations of two compounds will switch places, forming two entirely different compounds. So we have two ionic compounds, and these guys are going to switch partners. So now you see A is combined with D and B is combined with C to give you AD and CB, and this is an example of a double replacement reaction. So here's one that we've seen before. Lead nitrate reacts with potassium iodide to form lead 2 iodide and potassium iodide. Oops, that's wrong. This is potassium nitrate. Sorry. That should be nitrate, not iodide. There's a mistake there in my typing. Okay, so we see it. It's right on the chemical equation though. So we see what's happening. Notice this is a solid. So that means we've just formed a precipitate. Sorry. Okay, we also signify precipitate by a prefix, a shortened version, P, P, T. You will see representing a precipitate. Okay, so what does that look like? Well, first of all, let's talk about the fact that not all double replacement reactions produce precipitates. This is just one type of double replacement reaction. There are several, but this is one that we're going to be dealing with most right now in this section. Okay, notice we have two colorless solutions going into the reaction, and we mix those two colorless solutions in, we get this bright yellow solid. That bright yellow solid can't be anything but iodine, and you're like, well, how do you know that? Well, you have to understand some solubility rules. So how do we understand precipitate reactions? Because that's where we're going to be right now. We're going to go back and we're going to look at some other double replacement reactions, but right now precipitate reactions are where we're going to lie and where we're going to live at this moment. Okay? So precipitate reactions are really important to be able to understand. So we can see here we have two substances mixed together in solution, and this is the instant before they begin reacting. And then all of a sudden, here we have a compound on the bottom of the beaker, meaning if it's on the bottom of the beaker not moving, that means it's a what? It's a solid. And we see it here in the beaker. We see this kind of light whitish yellow substance there. So the formation of a precipitate is what we call a driving force for a chemical reaction. A driving force is just a sign that a chemical reaction has occurred. And we know some of those driving forces, and we're going to be looking at some of those in a demo tomorrow. Okay, so a precipitate is an insoluble solid that is formed when two aqueous solutions, I've got a lot of typos here, two aqueous solutions are mixed. We separate the precipitate from a solution by filtration. It was called gravimetric analysis. We are going to be doing this. This is the lab for this week. We are going to be doing the gravimetric analysis. Gravimetric analysis of a silver alloy. Okay, so you're going to be given a piece of silver, and you're going to be asked how much silver is in that piece of silver. Okay, and you're going to have to figure that out. So to identify the precipitate, you need to be able to predict which new substance will not be soluble in water. In other words, you must know your solubility rules. So you can go to your textbook, because there is a long list of rules in your textbook, or you can even look it up on the web. But I'm going to give you something a little simpler that hopefully will make you understand what you're doing. Now, I want you to understand as well, when you're on the AP exam, you can't say the trick for understanding solubility rules. You have to be able to say something about the fact that the energy of hydration is not great enough to overcome the energy of the crystal lattice structure in order to say why it's not soluble. That is the reason why it's not soluble. The reason why it's not soluble is not because of the solubility rules. The solubility rules are only in existence to help you remember those rules. So So use this table to help you remember the main solubility rules. So the table is knock L no so. If you say knock L no so, very silly, very simple, okay? Knock L no so. I remember these rules because of knock L no so better than I've ever remembered them before, okay? So Na, the Na part. Na stands for any alkali metal or group 1A and ammonium. So anyone that is a group 1A or ammonium are always soluble. So sodium, lithium, potassium, rubidium, cesium, francium, and ammonium are always soluble. If they're in a salt, they are going to be soluble salts. We use that a lot. We use that almost all the time. So there are two of these that we use all the time because they're always going to be soluble. And Nas are the first group that's always soluble. Cols stand for the halides. Okay, that's fluorine, chlorine, bromine, and iodine. The halides, other than fluorides are usually soluble because they're super, super reactive. So halides, though, of chlorine, bromine, and iodine are a little different. They are soluble except for those of silver, mercury, and lead. Silver, mercury, and lead. So I look at that and I say, okay, silver, mercury, and lead. I can remember those three. That's pretty good. I can figure that out. And I am trying to figure out what I did for that. So silver, mercury, and lead. Okay? Now, NOs stand for nitrates. The nitrates. All nitrates are always soluble. Every nitrate is soluble. This is the other group that we used often to make sure that we have something that is soluble. So we use NOs and we use NOs to make sure that we have things that are soluble. So things that are chlorides have to be NOs to be soluble all the time. Things that are nitrates are always soluble. So we can get even lead, mercury, and silver into solution with a nitrate. Okay, and then finally SOs. SOs stands for a little bit more than sulfates. You can also kind of apply these rules to hydroxides and phosphates, but in reality, hydroxides, phosphates, and other compounds are slightly soluble. As a matter of fact, usually the only ones of these other groups that are soluble are the Nas. The Nas are usually the only ones that are soluble. Every once in a while, you'll find one that's not true, but of these other groups, other than SOs, you're going to find that only the alkali metals are soluble for them. So chromates and phosphates and hydroxides and carbonates and all kinds of other things are going to play those roles. So just make sure you're thinking about that. Now, you can see that SOs have some more limitations. And the first one I call Cabossers. They are all those group 2 heavier elements, Cabosser. You can see why I say Cabossers. And then silver, lead, and mercury. Okay? And don't pay attention to that right there because lead 2s and sulfates are not soluble either. So just kind of stick to lead and mercury there. Mercury 2 is the one that's most common anyway. Okay, so mercury 2+. So, got that? I know, you're going to have to work with them a lot. You're going to have to work with them a lot to get those. But those are the main ones that you need to know. Okay? I'm trying to get an eraser because I know something's going to come up over top of this. Alright, so, here we go. Strong acids like hydrochloric and hydrobromic acid. I don't like that. I don't know why I can't get rid of. There we go. There's my eraser. Okay. Okay, now I've erased all the ink on the slide. Let me get my pen back. Sorry about this. I'm wasting a little time. Alright, so strong acids like hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric, we always write these as dissociated. What does that mean? Well, we write H+ and Cl- rather than HCl because they're strong, they completely dissociate. Now, strong bases also completely dissociate. So any hydroxides of group 1A and 2A metals, they completely dissociate as well. So weaker bases such as carbonic and sulfurous also break apart. So it's the moment these guys are formed, carbonic or sulfurous acid are formed, they break apart into molecular substances, and the substances they break apart into are these right here: carbon dioxide and water. Carbonic acid, H2CO3, is the acid that's formed in sodas, and you know this happens. You see it happen every time you crack open a soda. So when you're writing these on the AP exam and you get this as a product, you do not write this, you write this instead. Okay? Make sure you're thinking along those lines, because those things will completely and totally break down into these items immediately on palm forming at room temperature. All right, so those are some of the solubility rules. You're going to have to work with them a little bit. So have that page open while we do exercise 8. So when using solubility rules, predict what will happen to the following pairs are mixed. So here we go. We know if we mix KNO3 and BaCl, if we go through the prediction says, okay, this is double replacement, so I'm going to get BaNO3, and I'm going to get KCl. I didn't balance it. I don't have to balance it. I know something. This is a nitrate. What do we know about nitrates? They are all soluble, so this is going to be aqueous. KCl, well, that's a Na, so it is aqueous. All right? That means this reaction does not happen. There is no reaction here at all, ever, because everything is soluble. You can't tell if a reaction has occurred. Okay, so we go to the next one here. So what do we get? We get, let's see, PB is going to go with SO4, and since it's PB2, it's going to be PbSO4 plus Na and NO3, so that's NaNO3. Okay, I don't have to balance it. I just need to know what's going to happen here. Okay, I clearly know that this is going to be aqueous. It's a Na and a No. It's got double solubility on its side. Over here, it's a sulfate, but it's a lead sulfate. Lead sulfate is not soluble, so this reaction is going to happen, and it's going to form the compound solid lead sulfate. Okay, last problem. I have potassium hydroxide and iron nitrate. So again, I know what's going to happen in a double replacement reaction. I'm going to get FeOH3. Why is it OH3? Because I have a +3 iron here. Okay, and I'm going to get potassium nitrate. Okay, potassium nitrate, just like sodium nitrate, is a double solubility, so it's got Na and No, but we have a hydroxide here. Hydroxides are quite insoluble except for group 1A and some of group 2A. So this one is going to be our solid, so this reaction does occur. So of the three, A was the only one that did not occur. Okay? All right, so describing reactions in aqueous solutions. So first of all, we have to write a molecular equation or a complete balanced equation for the overall reaction. Remember, it just tells us the things that we need to know. It's the way we were taught in first year chemistry to do it. For some of you, we did start going into the next portions, but we didn't practice them as much. We practiced molecular equations a whole lot. The molecular equation can be really important, so make sure you write that down. The second thing that you need to do is do a complete ionic equation. That means you break everything apart into the electrolytes that they are. So anything that is not a solid, anything that is an aqueous solution gets broken apart into its ions. And we're going to do an example in just a second here. And then finally, the net ionic equation includes only those things that undergo change. So anything that just stands around in solution is not included. Spectator ions are not involved in the reaction process. They start as an ion and they finish as the same ion. This is important. If it's an ion on the reactant side and it's the same ion on the product side, it's a spectator ion and it will not be included in the net ionic equation. Okay, there's always conservation of mass and charge in net ionic equations, so you have to make sure that you're balanced and that your charges are 0. You cannot have an overall charge of a -1 on one side and 0 on the other. You have to have a charge of 0 on both sides. So you need to make sure that that is taken care of before you move forward with any kind of a calculation. On the AP exam, net ionic equations are the ones that are the most expected. Because we are boiling down, in a net ionic equation, we're boiling it down to the basics. what is the chemistry that is happening. We're not concerned with anything that doesn't do anything. We're only concerned with the stuff that is reacting. And so we're boiling it down to the essence of what is going on. And we'll be talking about that in class a little bit more. So exercise 9A. For each of the following reactions, write a molecular equation, the complete ionic equation, and the net ionic equation. So let's start. Remember, molecular equation assumes it's balanced. So we have to make sure it's balanced. So we start off with KCl aqueous plus AgNO3 aqueous. Okay, and that's going to give us, it says silver chloride, AgCl solid, it says it's precipitate, plus KNO3. Now we just have to double check and make sure that everything is balanced. So K, yes, Cl, yes, Ag, yes, NO3. Okay, so everything is balanced, so we're good. So that's the molecular equation. The complete ionic equation, a little bit harder. K plus aqueous plus Cl minus aqueous plus Ag plus aqueous plus NO3 minus aqueous yields AgCl solid. Notice I didn't break that apart. It's a solid. It's not an electrolyte. Plus K plus NO3 minus aqueous. I forgot the aqueous on the K. Let's squeeze that in. Okay. So there's our complete ionic equation, and it is also balanced. Now, I find balancing this is really easy. If I already have a balanced molecular, I just take the molecular and I balance it through the complete ionic. So the net ionic, remember, is going to get rid of spectators. So I'm looking for those things that are the same on both sides. So I see K and I see K. Hey, that's a spectator. It's the same on both sides. I don't need it. Cl, well, Cl is part of AgCl solid, so I can't cross that out. Ag is part of AgCl solid. Can't cross that out. NO3 minus, NO3 minus. There's my other spectator. Spectators are now gone, so I'm going to write my new equation as Cl minus aqueous plus Ag plus aqueous yields AgCl solid. And that's the answer. Pretty simple. Okay? So what's the next problem? The next problem is exercise 9B. It says an aqueous potassium hydroxide is mixed with aqueous iron 3 nitrate to form a precipitate of iron 3 hydroxide and aqueous potassium nitrate. So here we go. Our molecular equation starts off with our things. So we've got potassium hydroxide plus iron 3 nitrate. Yes, ladies and gentlemen, you're going to have to get really good at writing these formulas. You notice I almost write them without even thinking, and that's because I've been doing it for so long, but you're going to have to get there. So we get iron 3 hydroxide, and we're given in the problem that it's the solid. Now, eventually, you will have to figure that out. And then potassium nitrate aqueous. So now we have to make sure it's balanced. I see 3 nitrates and only 1, so I'm going to have to put a 3 there. I see 3 hydroxides and only 1. Put a 3 there. K's, all good. Okay, so then I go to the CIE. And this is where I use this equation to help me balance this too. It's not a big deal. So I have 3 potassium ions in aqueous solution plus 3 hydroxide ions in aqueous solution plus 1 iron 3 in aqueous solution plus 3 nitrates in aqueous solution. Okay, and that's going to yield my solid, FeOH3 solid, plus 3 potassiums in aqueous solution and 3 nitrates in aqueous solution. Okay, so there's our complete ionic. And all I did is I just took the molecular and I broke down the things that were in aqueous solution, kept the things that were solid. That's all I did. So it's not rocket science. It's actually pretty simple. So the NIE next, remember we have to get rid of the different things. So let me change my ink color again and get rid of what I need to get rid of. So I see 3K, 3K plus. They're gone. K plus is gone. OH minus, well, that's involved in my solid, can't cross that out. Fe, that's involved in my solid, can't cross that out. 3NO3 minus, 3NO3 minus. There we go. There we go. It's crossed out, so all my spectators are gone. So now I'm going to get my NIE. So 3OH minus aqueous plus Fe3 plus aqueous yields FeOH3 solid. So this is what we're really interested in, the basic. What needs to happen? I need to have a source of OH, I need to have a source of Fe, and I will make FeOH3. That's pretty much the essence. Now, is everything balanced? Well, I have 3 OHs, 3 OHs, 1 Fe, 1 Fe, but I also have to look at charge. There is 0 charge on the product side. It's a compound. It has no charge. But over here, I have 3 minus charges and 1 3 plus charge. So we have 0 charge on the reactant side too. So please make sure that you've done that, because that could be an easy way to double check to make sure you have those things right. All right, so almost finished. So how do we actually do this idea of gravimetric analysis? And I again made another mistake because I got pictures that I shouldn't have up yet. So we start by mixing 2 aqueous chemicals together to form an insoluble salt. Then we filter out the salt. We can do one by gravity filtration, which is this one right here. This is gravity filtration. We just have a funnel, and we have filter paper inside that funnel, and there's a clamp. Usually there's a clay triangle holding up that thing, and then we have a flask underneath it catching the water while the solid stays behind on the filter paper. That's gravity filtration. Then we have vacuum filtration, which is very similar. In vacuum filtration, we use a different kind of funnel. This is called a Buchner funnel. Okay, a Buchner funnel is shaped a little differently, and it has a collar here that fits very snugly into this vacuum flask filter. It's a vacuum flask filter because it has this little spout. Okay, that little spout hooks to a hose, and that hose hooks to the sink, and on the sink there's a little attachment onto the sink drain that causes a vacuum to be pulled into this flask, therefore pulling the liquid down from the funnel more quickly, and you're going to have a piece of filter paper up here that's going to catch all of the solid, and that is the way we do that. Now, vacuum filtration is quicker than gravity filtration. Fact of matter, it's quicker. So we have to understand those points. So then we're going to dry the salt to constant mass. And many of you are like, what do you mean, dry the salt to constant mass? This means we're going to dry once in mass. Then we're going to dry as many times as needed to be certain that the salt is really dry. What does it mean to be really dry? Well, we stop drying when the mass stays the same. So we are going to continue to put that thing in a drying location until the mass remains the same. So you might have to do it for 24 hours and then mass it. And then do it for 6 hours and then mass it. And then do it for 6 more hours and mass it. So you just need to keep massing until your masses stay exactly the same. So then we're going to use stoichiometry to determine any of the desired quantities we want. And I'm going to be putting up another video tomorrow night that will go through this process of what do I mean by using stoichiometry to determine whatever I want. We're going to be going through that process and looking at a couple of videos about that and solving some of those problems, so to make sure that you've got that. Okay? So exercise 10 says, calculate the mass of solid NaCl that must be added to 1.5 liters of 0.1 molar AgNO3 solution to precipitate all of the Ag ions to form AgCl. So the first thing I need to do is I need to write down a formula, a chemical equation. So I know I have these two things, and they're both aqueous solutions. Okay? I know that when I do that, I'm going to get solid AgCl, and I'm going to get sodium nitrate. Now, in all honesty, I don't have to go past this point. I don't have to go past the point of having this information. I can and do the CIE and the NIE, but for this problem, I don't really need to. I would go ahead and do it so you get the practice. So let's go ahead and do the CIE real quick. The CIE would be Na plus aqueous, Cl minus aqueous, Ag plus aqueous, NO3 minus aqueous, and that's going to give me AgCl solid plus Na plus aqueous and NO3 minus aqueous. Now the Nie, I get rid of all the things that are spectators. So here I go, getting rid of spectators by changing my ink color so we can see the difference. Na is a spectator. NO3 is a spectator. Okay? I'm just looking to see what's the same on both sides. That's it. That's all that I'm doing. So here we go. So we get Cl minus aqueous plus Ag plus aqueous yields AgCl solid. I forgot the G over here. Ag. Okay. And that's our Nie. So let's look at the problem. What are we given? We are given this. Remember, molarity is a way to take something from from liters to moles or moles to liters. So we're given that we have 1.50 liters of AgNO3 solution. We know that the concentration of the AgNO3 is 0.10 moles of AgNO3 to 1 liter of solution. Okay, so now I have liters of solution gone. Now I have moles of AgNO3. Well, I would typically, because sometimes you're going to have different mole values. Okay, and what I mean by that is AgNO3 has 1 mole of Ag in it, Ag1+. So we know that it has 1 mole of Ag1+. We also know that 1 mole of Ag1+ produces 1 mole of sodium chloride. Okay, now I'm just going, so now I've got moles of AgNO3 gone. I've got moles of Ag+ gone. Now 1 mole of NaCl over 58.44 grams of NaCl. Okay. And then I start calculating. Moles of NaCl are now gone. I've got grams of NaCl. And so I calculate through and I get 8.77 grams of NaCl. Okay? So I started with my given. I went through all of the process. This step right here, these two steps, could probably just be combined. That's why I said the Me is probably good enough, because in reality you just needed to know that for every mole of Ag you needed 1 mole of Cl, and that's what you have already. But for understanding's sake, probably a good idea to keep it. One more exercise, let's see if we can get that done. Alright, so when aqueous Na2SO4 and PbNO3 are mixed, PbSO4 precipitates. So we know that we have the Me is Na2SO4 aqueous plus PbSO4. Nope, wrong one. Sorry. It's not PbSO4, it's Pb something else, isn't it? Okay, so we get PbNO3 2 yields PbSO4. I'm going to put aqueous behind this one, and this is a solid, plus NaNO3 aqueous. So I've got a balance. I've got two NAs, I need 2 NAs. I've got 2 NO3s, I need 2 NO3s. I've got them, so they're in balance. So now I go to the CIE. CIE says I'm going to have 2 Na pluses aqueous plus SO4 2 minus aqueous plus Pb 2 plus aqueous plus 2 NO3 minus aqueous, yielding PbSO4 solid, plus 2 Na plus aqueous plus 2 NO3 minus aqueous. Okay, so now I need the Nie. The Nie, pretty simple. Remember, I'm going to get rid of my, so Na 2 Na plus and 2 Na plus are gone. 2 NO3 minus and 2 NO3 minus are gone. Now, you're saying, well, how do you determine that? I usually look at my product side. I see what I have still in aqueous solution, and I come over here and I compare it and I mark those things out. That's the easiest way to do it, but with practice you will get there as well. You will be as quick at it as I am, but you have to practice it. So now we have SO4 2 minus aqueous plus PB 2 plus aqueous yields PB SO4 solid. Alright, so now we have all that we need. It says calculate the mass of PbSO4 formed when 1.25 liters of 0.0500 molar PbNO3. We have two things. When we have two things, we've got to think limiting. So remember, when you're given two reactants information, you have to be thinking, I have to do a limiting problem. I have to be able to determine which one's limiting. So let's start there. I know I have 1.25 liters of the PbNO3 solution. Okay, and I'm going to convert that to moles by taking the 0.0500 moles of PbNO3 solution, okay, over 1 liter of PbNO3 solution. Okay, and I'm going to change that into moles of PbNO3 2. Okay, I'm going to do the same thing here, and when I do that, I end up getting 0.0625 moles of PbNO3 2. So down here I'm going to do the same thing, but I'm going to do it for the other reactant, Na2SO4, and I get here that I have 1 liter of Na2SO4 over 0.0250 moles of Na2SO4. Okay, and when I do that, I get 0.0500 moles of Na2SO4. Okay, now I need to change these to the other guy. I know you're like going, oh my god, I can't believe I have to do all this. So we have PbNO3 moles down here. We have Na2SO4 moles on the top, and we see it's a 1-to-1. Okay, so that means 0.0625 moles of Na2SO4. I can actually stop right here. Why? Well, this is how much I need to react with all of this, but I only have this much. This amount is less than the amount that I need. So that means that this is the limiting. So we have just found that the Na2SO4 is our limiting reaction. Here's our limiting reactant right there. So our limiting reactant is Na2SO4. So now I can do all of the rest of my problem with Na2SO4. I don't have to do anything else. I can keep it to Na2SO4. So that's the beauty. So this is my solution to my problem here. So I'm going to have 0.500 moles of, nope, 0.05, sorry, Na2SO4. And now I'm going to take this through my conversion. I know that I need 1 mole of Na2SO4 on the bottom, because moles have to go out, and I'm going to create 1 mole of PbSO4 from that, and then I have 1 mole of PbSO4, and I have 303.26 grams of PbSO4 in 1 mole, and then I get 15.2 grams of PbSO4. So that is the answer to my problem, and that is how it's solved. Remember, there is going to be another video up tomorrow night about solving these kinds of problems. How do I go about solving? What do I have to do? Don't panic, because tomorrow we're going to be practicing precipitate reactions and solubility rules. Okay? Thank you, young people.